Hello, everyone. Welcome to this session. I'm very excited to talk to you about some of the, probably some of the future that we can see with Spark. So Jules already introduced me. As we see these days, so we are talking about releasing Spark 2.3 either at the end of the year or a bit later. There is some talk to discuss about how to work on the Spark 2.4. And really, I think now it's time to start thinking about Spark 3, about the future. So this talk is more about a personal perspective from having used Spark after a bit more than 7 years now, and seeing really what I think have been some of the huge advantages that Spark have brought in the field of big data, and also some of the things that now we can start thinking about changing in Spark, in Apache Spark. So I'm by formation and by trade, I am a statistician, and I really like theory. But I really like this quote from James Maxwell, the father of electromagnetism, which is that there's nothing more practical than a good theory. So I hope here that I'll be able to give you some ideas about how some of concepts coming from functional programming and from theoretical computer science can inform us on how to build complex big data applications. And so if you look really at Spark applications, and if you're yesterday in the meetups or if you're at the keynote this morning, really we've been talking about the complexity and how the applications now get more and more complex. So the question is really about how we can deal with this, how we can deal with this complexity. So what I would like to discuss with you today is what kind of good foundations we can have for building big data applications. So let's talk a bit about how good Spark is and what are the trends that we can see in the process for building big data applications. So when we think about these days about big data, we tend to mention the term big data pipelines, really because we like this idea of having something which is linear, which has one input, which, if we want to be fancy, is going to be a stream, then some output in some things, and then if we want to show off, then we'll have some static data that we integrate and run some ad hoc queries on top of that. This is really what we like to think about. But the reality is already more complex than that. This diagram of multiple tasks talking to each other come from one of Databricks customers, and you can see that already it is not a pipeline anymore. It has some steps, forking and then joining again. And as we look at the trends, really, what we're going to deal with in the future, and it is actually already the case for a number of large companies, is having to deal with hundreds of import sources, thousands of different requests being done on a single system, and as we were talking before with Delta during the keynote, mixing the ability to mix interactive, batch, streaming queries all into a single system. And this is not really a pipeline anymore. Here, we can really talk more about the refinery, something really complex, something that needs to be maintained and for which different rules apply. And the question here that I would like to discuss with you is how we can enable this future. So as I was mentioning, the image of a pipeline really gives you the illusion of something simple and linear, with one input and one output. But already if you look at most of the big data systems, such as BigQuery, Kafka, Spark, then it is really following more the SQL paradigm, in which you can combine multiple sources, run a query, and then you get one output, or you can write this output. But if you look at the applications that people would like to do, usually they want to have multiple outputs. Yeah, they want to be able to get something and then be able to share it between multiple other stages. And this is really not the paradigm of the tree, not the line. This is the paradigm of the graphs, of the directed acyclic graph, also known as DAG. So if we look at what we would like to get from a big data processing system, really at a very high level, what kind of rules would we like to have? Well, one of them, of course, is scalability, because we like this system to be able to scale not only in terms of in the size of the data, but also in the diversity, having a lot of sources, having a lot of different sources, being able to be ingested into the system. Then come the chaining. So we like to be able to express the dependencies between the elements, because otherwise we need to manually remember that if we update a table somewhere, then we need to manually track all the dependency that this table will incur and know what we need to do. So some systems can do that, but it's still fairly limited. Also, we like to be able to compose, and this is something that lacks in most of the existing systems these days. We would like to be able to write smaller subsystems and assemble them into a larger one without having the complexity of the underlying subcomponents transpire at a higher level. And finally, I think even though it is not really required, it is very convenient from a developer perspective. We like this system to be deterministic, and by this I mean if you have the same input and the same program, you should always have the same output. And as we'll see, some of these big data systems do not necessarily allow you to do that. You may have different outputs given the same set of inputs and the same program. So how is Spark doing so far? So you can say that it does all of that already, but it's really hard. In the same sense that you can say that you can write any program in assembly code, and it is true, but it's not really easy to use, and it's not easy to maintain in the future. So if you look, for example, at this small program coming from one of our customers, which is about dealing with ads, you'll see some of the typical pitfalls that plague most of the programs, not only in Spark, but also in most big data systems, which is that it interleaves some declarative parts, saying, I'm going to read, for example, the source from JSON, I'm going to cache it, and then I'm going to do some manipulations, and eventually I'm going to write the output. And in between, it can take a couple of hours to do something. But a number of things can go wrong here. First, there is a typo, and you'll probably notice this typo after a couple of hours of processing that you need to trash because this program has no notion of being able to rerun and reuse some of the existing work. There is, for example, also another case, a missing directory. You didn't create output tables, and so it is going to crash again after you fix it. And here, in the process, of course, you decided to cache all these tables, and Spark will happily cache and cache again the same input, and we are not done caching it. So it might leak, and then it might cause some problems for some other parts of the pipelines, and it will be hard for you to realize that the leak comes from here. So after all, this is all fixable. This is all easy things that everybody can learn about and can eventually fix. But going through the cycle of debugging and fixing all these issues will take a while. And really, would there be a better way to be able to have a better interface that would prevent you from doing these mistakes in the first place? That would be able to tell you in the beginning all these mistakes, even before you start to run your program. So this is what I call the 4 horsemen of the datapocalypse. So typically, it is going to be schema mismatch, so essentially typing problems, missing inputs and missing outputs, so being able to deal with I/O, resource leaks, being able to deal with all the table that you create and you remove, and also that should be temporary in your program. And finally, eager evaluation, which forces your program to execute before really you need the output in some place, really forces you to only have results after a long time, or even wait for days before you can see failures after that. So let's see how some other fields in computer programming, like functional programming, can help us here in that respect. So I want to discuss a bit with you here some theoretical foundation that we can put for describing a system that can ingest and process data. So one way to think about the data set is really a collection of elements that are all of the same type. So in Scala, it would have this signature. And one principle you can say that this data set lives somewhere, and you cannot really see what is inside except by doing some queries against it. So you cannot poke directly inside the contents of this data set. And when you make a query, you don't necessarily get immediately the result. You get a box that will contain the result, an observable. You can think about it in the world of SQL as being another data set with just a single row. And you can then manipulate this observable, so this result, without having necessarily to observe the content of it. So here is actually what it would look like in a schema. So you have this big data set with a number of political personalities and the size of their hands. And so you could observe how many there are in this data set, what is the size of the largest hands in this data set. And also you can, so that's really querying the data set. That's making observations of the data set. Another thing you can do is take the data set and transform it. So for example, here, you can transform it in time and see what they become. That's another transformation. And then you can do some other observations on this data set. So really, these are the two fundamentals operation that you can do on the data set. Either transform it, or join it with some other data sets, or observe things out of it. And one principle we can say when you observe a data set is that the content of the observation so the observation itself will only depend on the content of the data set. You should not be able to observe how the data is being laid out, and for example, in the case of Spark, how many partitions you have, how the elements are being ordered inside the partitions, how are they on disk, are they on memory, and so on. The observation should not depend on that. And in the case of Spark, for example, this is not the case. And I'll be talking about it more in details later this afternoon when talking about graph frames for actually some of the issues that it caused developers by having the ability to observe, for example, the number of partitions. So we should not be able to do that. And also it has some very nice mathematical consequences if we do that, because then all the operation that you do on a data set to observe it can be essentially reduced to a set of, so all these operations obey a very strong set of primitive mathematical operations, which in this case here, if they are also associative, that means you can put some well-known structures on top of these observations. So another principle that would be nice to follow is the idea that all the effects that a data transformation has with the world can be modeled within the system. So if you look, for example, at Spark, you can do a number of things which Spark doesn't really track. For example, if you write to a file, then Spark will happily stop the program, run it, write to a file, and then let you continue after that. It doesn't really track the fact that you wrote to a file, and so when you read the file again after that, it will not capture the notion of dependency of the fact that you wrote something first and then you are reading it later. And as we'll see, it will be if we can track all the operations such as reading and writing, then we can really track the dependencies that happen between different parts of a pipeline, and then we can actually optimize a number of these dependencies independently from what the programmer wants to tell us. And we'll see what kind of checks and optimization it lets us do after that. So what kind of operations can we run with this kind of system? These are all the ones you would expect. So if you take, for example, a data set of integers, you can compute the maximum. Then that is going to be an observable, which will contain an integer. If you collect your data set, you're going to get a list of integers. And again, this is going to be boxed inside an observable. So it may not necessarily run immediately. So all of these principles can be implemented by doing some slight modification to Spark. And so I would like to present to you a prototype of these principles here, of this implementation. So I wrote a small project called Carbs, which essentially takes a Spark program and which lets you express all these operations, and then it outputs graphs of logical plants to Spark, or some other systems for that matter. And it will do a number of extra correctness checks on your program that are right now not available in Spark. And also it can automatically perform some optimizations that, as most programmers, you would know that you would want to do, but are mechanical, and really that you should not bother about doing yourself. And actually, as a consequence, you can take a limited subset of pandas, the Python library, and automatically have it work on Spark. So let me show you what it looks like in practice. So if you have used Spark on for doing some processing, you probably had at some point to write some aggregate functions. So given a data set, you want to be able to do some more complex operation than min, max, collect, and a few of the operations that are defined in Spark by default for doing operation on these data sets. And let's take an example here on this Databricks notebook. So let's say that I want to implement the harmonic mean, which is one of the means which has some nice mathematical properties, and it is not available in Spark. So it has a nice it has a nice mathematical formulation like this, and it is really easy to write as these functions here. So if you take a column of a data set, then you can count how many elements you have in this column. You can compute here the inverse of the sum of the inverse, and then you can multiply this. This is exactly what this formula is being done here, and I rewrote as a tiny Spark program. So this is all the operation you are used to: sum, count, and then division, and so on. And of course, and then you can check that it works using pandas, for example. And yeah, so it gives some result. Then of course, you can run it against a Spark data frame here, which is wrapped. And if you want to, so of course, if you see this program here, even if you are a Spark expert, you're going to say a couple of things. The first one is this is going to run sum, this is going to run count on this data set. So really, what we should do first is, because it's going to run twice against it, we should cache it to make sure that the computation that generates this data set is not being rerun. And so here we have this auto-cache function. You'll see why it is called automatic cache instead of simply caching, because it will do some extra checks for you. And at the end, so also one thing to notice here is that I applied my function, and it did not compute any result. It just told me, I'm going to return to you an element, a double, and which is actually called multiply because it comes from the last multiplication we did here, but it didn't run it. It just said, OK, this is the final result you'll get, and then you need to do some extra steps to actually compute it. So far, everything is lazy, and nothing has executed. So now let's execute it. Let's open a Spark session, and then we're going to run these computations here. So if you look at the so these computations are going to run in the background, and if you look at and also now we can look at the graph of computation being run here. So it starts from my data set here, this input, then it caches it, and as we were talking before, it is going to run on one side, it's going to compute the sum, and it's going to compute the count. And if you are Spark, and then eventually it's going to return the multiplication here, the final result. So if you're a Spark expert, you're going to say, OK, this is not how you write a good Spark program, because really you should be able to compute the Spark, the sum and the counts automatically. And since here we have you should be able to combine that into a single pass. And since here we have access to the whole program, we can really do a number of optimization that users are right now being forced to do. So for example, one thing we can do is making sure that this sum and this count happens at the same time, just in one pass. And this is what is being done. So here you can look. So by the way, this visualization comes from TensorFlow. It is one of the tools being used for developing this kind of for developing neural networks. And so here I took our first graph, and I generated, and the program behind the scene optimized it in such a way that now, instead of doing sum and count separately, it is doing both at the same time, and it is going then to so it is doing both at the same time in this more complex aggregation, which I didn't need to write as a programmer. This is all generated for me. And then after that, it is going to do still the multiplications. And so now that we do only one pass like this, do we need there's still this caching node here, which instructs Spark to cache the data set. But now, do we really need to cache? Because we're only doing one pass over the data. We don't really need to cache anymore. And this program is analyzed again to remove this caching step. And if you look at the final graph of computation being run, then you'll see that the caching step here has disappeared. Because the program could the program could infer that all the caching operations are not necessary because we are just doing one pass over the data set. And finally, then you get the final results here. So I hope this small example motivates a bit how you can write then high-performance programs without having to go down to the low level. Here, this was all done in Python on a simple notebook. And behind the scene, it took a fairly, you'd say, poorly written program in Python, and we wrote it in something that is nearly as efficient as you can write without having to go down to Scala, without having to go down to really low-level primitives in Spark. It is doing all this mechanical transform for you. So really, it enables us to do lazy construction of very complex programs. And when you look also at all the operation in Spark, nearly all of them can be translated into a very small set of primitive actions that follow all the rules I described before. So then we can rewrite these programs automatically without changing the outcome. And then the SQL optimizer can take care of further optimization to translate it into nice hardware-optimized instructions. But this, so this really helps us for optimizations. Let's see now how it can help us also for doing for writing more complex programs. And if you're like me, you probably at some point wanted to write a program that had some that not only was that was an aggregation function, but this aggregation function was too complex to express, for example, within the context of UDAFs. And here I want to have a small example with you based on the birthday paradox. So you probably heard about the birthday paradox. Given the number of people in the room, there is probably at least 2 people in this room sharing the same birth dates. So and we're definitely way too many so that we can run the experiment here. But we can write a small Spark program to compute that. So let's start here from a data frame that contains company names, name of people, and then birth dates. And let's compute how many, for each of the companies, how many of employees in each of these companies share the same birth dates. So you could write a SQL statement for doing that, and it could start to be fairly complex. But really here, I want to show you how you can decompose your problem into multiple pieces. Because really here, what you want to do is, given a set of birth dates, being able to compute how many of these birth dates share the same, how many of these employees share the same birth date. And then when you think about it, this is going to be an aggregation function, because it takes a data set of birth dates, and it returns to you a number. So why can't we use it inside as an aggregation function in a larger program? And this is what we're going to do here. So this is a function here that, given a column of birth dates, so it returns the number of employees that share the same birth date, and it really corresponds to standard operation in Spark. So it groups elements by dates, and then it filters all the groups that have. It keeps only the group that have more than 2 people, and then finally it makes the count of all the people inside these groups. So that's really what you expect. And we can also test it, for example, against a small pandas data frame. So here, I have 3 birth dates. 2 of them are the same. So hopefully, yeah, it gives 2. Perfect. Now let's use this function here, paradoxical count. Let's use it against a Spark data frame. And let's use it against our original data frame that also contains the employees. So all I need to do here is take my employees data frame and aggregate and grouping. I can group the elements by company name, like you would do in Spark, like you do in PySpark. But then I can directly plug the function I wrote as an aggregation function. And Spark would not let you do that, because Spark here would tell you, this is not a UDAF, this is not the transformation I know. This transformation is too complex for Spark to express directly. But in this model, since thanks to the laziness and the determinism of the program, I can actually rewrite the plan that corresponds to this function, and I can insert it into a larger plan that has also keys and grouping around it. So I'll not go through the all the transform that happens. So yeah, after that you can run the computation. It will return the result that you expect. And if you look at the plan that is being done in this program, you'll see that we start from this employee data set here, and then we're going to do an aggregation. And this aggregation, instead of being a simple function, will have this much more complex function here, pcount. That is the function I just defined. And inside it has a number of steps. So it has, the filtering step, it has the final shuffle, and so on. And if you look at each of these operations, and if you look at the construction of it, then you can actually rewrite this query plan into something that Spark can understand. And if you look at the final plan, it corresponds to the plan that you would write manually in SQL, with all the steps. Actually, in this case, happens to be just a linear plan here. And finally, when you run it, you can also have some other information that are available, because here it really gives you a top-down view of what your program is doing. So if you were to look at Spark, if you were to look at the outputs of what Spark is doing, you could look at the physical plan, and you could say, okay, this shuffle here is particularly slow, but where does it correspond to? And Spark here would be able to tell you, okay, this stage here in this job is particularly slow, and all you know is that it has an RDD called shuffled row RDD ID 91, and then good luck to figure out what it corresponds to in your program. So now that we have a declarative interface for expressing our program, and now that we can compose elements together, actually we can have really a top-down view of the computations. And you can also combine this graph of logical computation with the graph of RDD computation that Spark is going to run. So here, if you look at the graph of RDDs that Spark is going to do, you can drill down into the operation, and you can find, for example, that this shuffle row RDD that we're talking about, it was generated by this node called here particle employee inside this function here. So that means that you can quickly identify within your program that it was this sum here, for example, that would cause some slowness here. So it provides a lot of information in terms of debugging at a much higher level than what Spark can offer. So, of course, this is really a prototype. There's a lot of things that needs still to be done in order to make it production ready. One of them is probably the most important, is going to be adding in Python interface for describing inputs and outputs. And there's a lot of very interesting things that can be done to optimize these operations. And also adding more information about tracing and profiling here, as well as integrating with SQL. So to come back really to what we talked about here, I think the question that all these big data systems are going to have to face in the next couple of years is how to manage really complex workflows that need to be decomposed and integrated into multiple pieces, and that need to communicate their inputs and outputs between multiple phases, and how we can reuse some of the existing components within a much larger set. So Spark provides some really strong foundation for doing that. And if we add some notion of laziness and more declarative API, I think we can alleviate a lot of this complexity. So you can try this demo. It is all available as open source code on GitHub. And the notebook is also available there for both Databricks and Jupyter if you want to try it out. OK, thank you for your attention. And I think we have just enough time for a couple of questions.
Tim. We have actually about a minute to answer any questions. There are two mics next on the aisle over there next to the camera. So if you have any question, please walk up to it and ask yourself. Make it succinct, make it short, because we only have about less than half a minute. Any questions? All right, no questions. Give a big hand to Tim.